Hey, thanks everyone for coming to the talk. I'm Binghui Peng. I'm going to talk about our recent work on the complexity of equilibria in first price auction under general tie-breaking rule. This is a joint work with Chen. So in a first price auction, there's a one atom to sell, and there are n players want to bid for the atom. In particular, this player will submit their bids simultaneously, and the atom is sold to the player with the highest bid, with price equals to her bid. This is the most fundamental format of auction, and the study of a first price auction dates back to the seminal work of Victory in 1961. It also have numerous applications in real life, including application in sealed bid auction and also application in search engine auction. The first price auction is usually studied in the Bayesian setup. That is, we assume there's a prior distribution D, and for each player, its own price value Vi is drawn from the valuation distribution Di, and this distribution are independent. The prior value Vi is known to a player I, but it's invisible to other players. But the prior distribution D is a common knowledge for all the agents. For player I, its bidding strategy is a mapping from the private value Vi to her bid. For the allocation, giving a bidding profile from these n bidders, the allocation rule satisfies that it allocates the good to the highest bidder, and and the other bidder just get nothing. The highest bidder is charged with the payment equals to her bid. There's a long line of literature for first price auction, partially because the first price auction is like a historical landmark for economic literature, and the people tries to characterize the equilibrium behavior for first price auction. In the past decades, the problem also attracts people in the computer science literature, and people study the equilibrium computation and also the price of anarchy of first price auction. One fundamental concept of game theory is the incentive. That is, we assume all the agents involved in the auction or in the game wants to maximize his own or her own utility. But in terms of first price auction, despite its wide applications and the historical reason, it's kind of like the most famous or the most infamous auction format that is not truthful. That to say, in a first price auction, no one really wants to bid its own value, because if one bids its own value, then even if it gets the good, its utility equals to 0. Because the first price auction is not truthful, so this motivates the study of equilibrium behavior in first price auction, and people wants to figure out what exactly people would, the agents or the bidders would do in a first price auction. Now let me formally define the concept of Bayesian Nash equilibrium in the first price auction. First, for player I, its utility equals Vi minus Bi times gamma I. Recall gamma I here is the allocation. So in particular, if the atom is allocated to player I, then gamma equal to 1, and the utility is Vi minus Bi. This is its value minus the bit. Otherwise, gamma I always equal to 0, and the player I receives 0 utility. In a Bayesian Nash equilibrium, the strategy profiles guarantees that for each player I, it does not have any incentive to deviate its current strategy, given other players' strategy are fixed. That is, deviating to other strategy would not increase its own utility. One can similarly define an approximate Bayesian natural equilibrium. That is, no one has incentive to deviate from its current strategy by giving other players' strategy fix up to an additive factor of epsilon. So here we would normalize the input and assume the valuation distribution is supported between 0 and 1. So finally, we usually make two rationale assumptions in the literature. First, we would assume no one would overbid. That is, no one wants to bid higher than his current bid. This is very natural because if one bids higher than her value, if he gets the atom, then it will pay more than his valuation, so it will receive negative utility. The other assumption is essentially without loss generality, and we assume the strategy is monotone. That's to say, the higher the price value, the higher the bid. Okay, there's a one missing piece from the above description. That's the tie-breaking rule, which I believe is the most tricky part of a first price auction. Recall in a first price auction, the auctioneer assigns the atom to the player with the highest bid. But what if there are more than one highest bid players? In that case, we need to break the tie and allocate the good either randomly to these players, or we divide the good to these players. There are many different choices in the literature. For example, people consider uniform tie-breaking rule where the goods is allocated uniformly to the players. You also consider running a second round of liquid auction. That's to say, essentially the good is allocated to the player with the highest bid and also the highest value. Other choice also including set up a monopoly that always win if she is in the tie. And people also consider assign lexical order to the player. And for players in the ties, the atom is allocated to the one with the highest lexical order. So in this work, in order to formally study the computation complexity and capture the generosity of first price auction, we assume the tie-breaking rule is embedded as part of the input. Okay, one amazing or fascinating or like challenging thing of Bayesian natural equilibrium in first price auction is that it usually denies the intuition. And I think the reason is mostly due to the bidding space is continuous, so it's an infinite action game. So first, Bayesian natural equilibrium actually may not always exist, and even under very simple examples. So here's one example. Suppose there are two bidders. The first bidder have value distribution uniform over 0 and 1, where the second bidder is always supported on 0. In this case, actually, there's if the ties break uniformly at random, then there's no natural equilibrium. The reason is that the first player always wants to beat the smallest value that is greater than 0. But unfortunately, that value just does not exist. So Bayesian natural equilibrium also does not exist. Here's another example. So I want to provide an example showing that actually Bayesian natural equilibrium could be very complicated and very strange, even under very simple value distribution. So here's the example. Again, there are two players and they have the same distribution that is supported uniform over 1 and 2. After some calculations, one can show the equilibrium is symmetric, and in the equilibrium, if the player has value 1, then it wants to bid 1. However, if it has value 2, then it wants to bid x with probability proportional to 1 over 2 minus x squared, where x is any number between 1 and 1.5. So under this very under this very simple valuation distribution, the equilibrium is quite complicated and quite strange. People have studied the equilibrium computation for many years, especially for economics. They try to characterize the equilibrium, like the existence, uniqueness, and further also try to provide a closed form solution. But Unfortunately, the closed form solution only exists in very special case, and in general, people feel it's very hard to give a fully closed form calculation. That's kind of approach taken by economics and mathematics. In the computer science literatures, one can view the problem from the computation lens and study the problem of equilibrium computation. That is, we want to figure out whether finding a Bayesian equilibrium is easy or hard. And in this paper, we address this perspective, and we study the computation complexity of Bayesian equilibrium in first price auction. We make one minor changes of the setup. That is, we assume the bidding space is discrete. That is, we assume each bidder chooses her bid from a discrete set B1, B2 to Bn, where we always assume B1 equal to 0. That's the bidder have the right to bid 0. This setup is actually first formally proposed by the work of Ruskas in EC 2021 in order to formally study the computation complexity. So now the output is some discrete values, so one can formally study the computation complexity on it. And this change I want to justify is actually very practical, because in real life, the money is actually discrete, not continuous. And also it's very general, because if one only wants to approximate Bayesian equilibrium, then this is without use of generality, because one can always discretize the bidding space. And lastly, on the discrete bidding space, the problem is quite well behaved. For example, Bayesian equilibrium will always exist with discrete bid, because it's a finite action game. The work of Ruskakis showed exactly PPAD hard to find an epsilon approximate Bayesian equilibrium for some constant epsilon, but under the subjective prior setup. In the subjective prior setup, each player have different view of the valuation distribution. So strictly speaking, it's not like a commonly Bayesian setup, because every player have different belief of the value distribution, and the most work in the literature consider common prior as in our work. So in their work left open the problem of computation complexity of Bayesian equilibrium for price auction under the common prior. The main result of our paper is to provide a computational barrier for first price auction and make some progress to their open question. So our main result is we prove a PPAD harness to find an epsilon approximate Bayesian equilibrium in our first price auction under a trilateral tie-breaking rule for some polynomial small precision. So here for a trilateral tie-breaking rule, the tie break, if there are less than 3 players in the tie, then the tie breaking explicitly described in the input. Where if there are more than 3 players in the tie, then the atom is allocated uniformly at random to this player. So the main takeaway of our work is that the equilibrium computation of first price auction is computational hard in general. And this hardness result also gives some explanation for the very slow progress from economic literature on fully characterized and closed form solution approach to equilibrium. On the other hand, we also give some positive results. For the uniform tie-breaking rule, we present a p-test. That is, for any constant epsilon, we give a polynomial time algorithms compute a constant approximation, epsilon approximation Bayesian equilibrium under the uniform tie-breaking rule. Recall that in the paper of Ruskakis, they show that PPAD hard even for constant approximation under the subjective prior. So combining our result and their result, we show a separation between common prior and subjective prior. And this result also kind of show that proving harness is more challenging in the common prior setup. And on the positive side, if you are satisfied with say 0.1 approximate equilibrium solution, then there exists a polynomial time algorithms by this result. In the rest of the talk, I will focus on the first part, that's the harness, and I will give you an overview of our reduction. So we would reduce from the generalized circuit problem, which is common in the literature. And the main challenging of the reduction actually arises in twofold. So first, the allocation and the utility function actually involves exponential number of bidding profiles, because when you compute the allocation or utility, you need to take an expectation over other players' value. So there are exponential number of such profile, and in general, there's no closed-form solution. And the only way I know how to compute this exactly is via dynamic programming. And second challenge is that in the common prior setup, the game is highly symmetric. Agents have the very simple and also the same utility functions, and each player almost fit the same bidding profile except removing itself. So from a high level, our conceptual solution is try to make things simple and linearize everything. To make things more formal, let me introduce the basic setup of the reduction. So in our reduction, we assume the bidding space only considers 3 bits. One is the 0 bit, and the other bit is 1 over n to the 4th, and the last bit is the 1 over n squared. For each player, the valuation distribution is divided into 4 parts. There's a large probability mass around value 0. There's a delta probability mass around B2 and B2 minus epsilon. There are probability beta mass over B2 and B2 plus epsilon. That's different for each player. And finally, there's a probability mass delta over 1 minus epsilon and 1. And then it's also uniform there. So from a high level, the hard instance has some layer structure. It has large probability mass around 0, and it has some different probability mass around the value point B2. That is where we encode the circuit, and also has some small value distribution around 1. Okay, so recall that in our layered construction, there's a large probability mass around 0. So from the view of player I, it's very unlikely that 2 other players simultaneously bid non-zero bit. That to see, we can remove this higher order term arise from the expectation. In particular, let Pij be the probability that player I bids Bj. Then the allocation function can be approximate as follow, which is a linear form of the probability Pij. This allocation function is derived by ignoring the case that more than 3 players have non-zero bid, and only enumerate the case that 1 or 2 players have non-zero bid. Okay, now let's let tau I be the jumping point of player I, such that the value at the point of tau I, player I bids B2 instead of B1. So because the strategy is monotone, tau I has one-to-one correspondence between Pi1 and Pi2. So just by equilibrium condition, we can write down the jumping point and need to satisfy the following expression. But remember, even after removing those higher order terms in the computation of allocation, the allocation function is still some very complicated linear form. And if you really plug it into the equation for jumping point, it could be very crazy. So our final idea is to perform a first order approximation. In particular, the high-level intuition is that if the jumping point lies inside a small interval and also with small probability mass, then we can perform a first order approximation to the above equations. So after some calculations, eventually we can reduce it to some fixed point problem. And this fixed point problem is quite standard for reduction, and one can map G, which is a n by n matrix, to the circuit graph, and F maps to the gate of generalized circuit. But unfortunately, there's still one subtlety here, is that the matrix G here has some certain properties, and the the function f here need to be monotone. So, but under this kind of properties, the fixed point problem is not so general, and actually it's not pretty hard. So that's the place where we need the trilateral type-breaking rule, and by incorporating the trilateral type-breaking rule, we can make it to be a very general fixed point problem, and finally reduce from generalized circuit. Let's finish the high-level description of a reduction. And at the end of the video, I want to give some open questions. The first question is the computation complexity of uniform type-breaking rule. So in our paper, we give a p-test, that is, we give a polynomial time when the approximation is some constant. But it's a very nice question it's a very nice question if one can figure out the computation complexity when epsilon equal to 1 over poly n. That's you want to find a very kind of like high precision equilibrium. And the same question can be applied to the different type breaking rules, like the VQ rule and also the indexing rules. Okay, and finally, our algorithms have very large dependence on 1 over epsilon. So it will be nice to give a efficient algorithm that works in practice. And thanks. I want to thank everyone for watching this video.